Hello again, and welcome to another installment of the final exam review for Calculus 3208 presented by CDLI. And today we're going to look at the first installment from our Unit 3 on rational functions, graphing them and all the details. This is our first installment from this unit. And keep in mind that this section, for most of you, are probably looking at your pre-calculus textbook, pre-calculus 12, and it'd start with section 9.2 for this business. And this is our 17th overall installment for our review stuff. So let's, without further ado, talk about the details here. We're going to look at how do we find all kinds of stuff for rational functions. We want to get all the point or removable discontinuities. We want to get all the intercepts, so all the places we touch the x and y axes. And we want to find all the asymptotes, be they horizontal, vertical, and or oblique. So this very short unit, which is our Unit 3, what it does is it sort of takes into culmination all the things that we talked about with limits in the last section, as well as some of the things we learned about polynomials from our 3200 course, which was your first unit there. Alrighty, so let's jump right into the business. We start with an example. It says finding discontinuities and asymptotes. So we're going to start by considering the function that's given right here. So we've got a cubic divided by a quadratic. So the first order of business there would be to rewrite that in factored form. And yes, I'm very kind. I've done that for you. So this is written in factored form as we see right here. So we get x plus 4 over x minus 5 times x plus 5. And then the denominator is x minus 5 times x plus 3. So we have to look for all kinds of important stuff. So first we're after discontinuities and asymptotes. So let's start by looking at all those factors and what we can do with each one of them as we sort of move through this stuff. So let's take a look now. If we look at here, we've got an x minus 5 and an x minus 5 that we can sort of eliminate from our equation, and that'll give us x plus 4, of course, and that's going to be multiplied by x plus 5 all over x plus 3. So not much algebra yet. And so we see that there are two non-permissible values for this function. We're going to have a non-permissible value at x equals 5. So we're going to say we're not allowed to be 5. And we have a non-permissible value at negative 3 to account for these two factors of the denominator. The one that cancels out, we should remember, will tell us what our removable or point discontinuity is. So that'll be at x equals 5, and we'll have a vertical asymptote at x equals negative 3. We should, however, if we're going to be particular about how we put these things together, we should find the y-coordinate that goes along with this guy. So there's going to be a point that we could find using the new version of the equation that this graph would approach coming from both sides. However, we're not really going to have that point on a graph. We leave a little hole in it. So if we fill x equals 5 into there, we could see that we're going to get 5 plus 4 gives us 9, multiplied by 5 and 5 are 10, and all of that would have to be divided by 5 plus 3, which is 8. So we have 90 divided by 8, and of course we can reduce that. That's going to give us 45 over 4. So that's going to be a point at 11.25 roughly. So at about 11 and a quarter for y. So we have actually a removable point discontinuity is at 5 and 11.25. Remember, that's not a point, it's a non-point. All right, so let's look at our horizontal asymptotes now, or oblique, depending on what we get here. Already got our vertical and our discontinuity. So in this case, horizontal asymptote or oblique, always about comparing the degrees of the numerator and the denominator. And in this case, the degree of the numerator is greater, so that tells us we have no horizontal asymptote. So if we have no horizontal asymptote, we have to double check to see if we're going to have oblique. And although the degree of the numerator is greater, its degree is 3, and the degree of the denominator is 2, giving us just that magic difference of 1, which tells us that yes, indeed, we are going to have an oblique asymptote. So let's find the equation of our oblique asymptote. And in order to get that, what I have to do, remember, is take our new version of the function that we have over here, and I've got to actually divide x plus 3 into this numerator. So I'm going to expand my numerator there, x plus 4 times x plus 5. So that's going to be x squared 9x when all is said and done, and 20, and that's all over x plus 3. So I do my synthetic or long division. Let's pick synthetic division. It's quicker and easier, and whenever we have a linear divisor on the bottom, it's a good idea. So we've got 1, 9, and 20. That represents all of the coefficients that we had. So we drop the 1, multiply by -3, add them up to get a 6, multiply by -3 again, and we've got -18. Add those together, and we've got a 2 for a remainder. So that means our oblique asymptote is going to have an equation of y equals x plus 6, stealing our coefficients from down here. So in terms of discontinuities and asymptotes, things we have: vertical asymptote at x equals -3, no horizontal asymptote, oblique asymptote at y equals x plus 6, and we got to punch a little hole in the graph at 5 and 11 1/4. All right, now we're going to take that same function, one we've just been working on, and we're going to find all the intercepts. So all the places it touches our x and y axes. So we already had it in factored form, so from our factored form we know that this stuff is gone. Now, the thing I always tell my students is that you get your x-intercepts, first of all, by looking at roots of the numerator. But don't be fooled by this guy. That one doesn't count. Remember, that point doesn't even exist on our graph, so it can't be an x-intercept. So to get x-intercepts, we just want x plus 4 by x plus 5 equals 0, and the roots of that numerator will be at x equals -4 or -5, giving us two x-intercepts, one at -4 and 0, and the other at -5 and 0. So if I were to draw the graph, I'd have to plot those points to help me get started. Then we have to find the y-intercept. Great thing about the y-intercept is I can pick this form to work with or this form to work with. It doesn't really matter. It'll always give you the same answer in the end. The y-intercept occurs, of course, remember, when we let x equals 0. So if I fill that in, this is probably the easiest form in this case to work with. All these terms with x's in them, since x is 0, they're all going to be 0. We get -100 divided by -15. So our y-intercept will be at y equals -100 over -15. So that's going to be 100 over 15, because a negative over a negative is a positive, and 100 over 15 can be reduced. 100 divided by 15, we reduce both of those by dividing them by 5. We get 20 over 3, which is about 6 2/3 if you're going to try and draw that on a graph. Okay, so we found our two x-intercepts, and now we have our y-intercept. X is 0, y is 6 2/3 on the graph. So those are all the intercepts that we would need to help us sketch that rational function. Let's look at some examples. First one, provide a complete analysis of this function. Same stuff, more practice. Here we go. Let's look for, first of all, any point discontinuities and any asymptotes. Can't factor that numerator. X squared plus 2 has no factors, and it's also got no roots except for imaginary ones, and we don't deal in that business here. So in the denominator, I can factor x plus 2 times x plus 1. So what that tells us is we're not going to have any point discontinuities because there's nothing fancy to cancel. So with no fancy canceling going on, we're going to have two different vertical asymptotes for this guy. So a vertical asymptote at x equals -2, and another one at x equals -1. So there's our vertical asymptotes. Let's look for horizontal and or oblique asymptotes. If we look at this function that we have over here, same degree on the top and the bottom, yes sir, we get a horizontal asymptote. So no oblique this time, but we do get horizontal. And our horizontal asymptote we find by taking the limit as x goes to plus or minus infinity. So we'll take positive for now. X squared plus 2 divided by x squared plus 3x plus 2. And we should remember that when those degrees are the same, it's just the ratio of our leading coefficients. And since they're both 1 here, we get an answer of 1 divided by 1, which is 1. So our horizontal asymptote is a horizontal line, y equals 1 unit above the x-axis. All right, so there's our vertical asymptote, horizontal asymptote, no point discontinuities, no oblique asymptotes. Let's get some intercepts. If we were to have x-intercepts for this function, they would have to occur at roots of the numerator, x squared plus 2, but unfortunately x squared plus 2 is never equal to 0 because we can't take the square root of a negative number, not in the real number system. So for x-intercepts, this graph never touches the x-axis. Alrighty, let's look for a y-intercept. So to get our y-intercept here, what we have to do again is evaluate f of 0. So if x is equal to 0, we're going to have 0 squared plus 2 divided by 0 squared 3 times 0, and again plus 2. So we're just checking these last two numbers as always. 2 over 2 is 1, so our y-intercept is at 0, 1. Full analysis, no x-intercepts. Y-intercept is 0, 1. Horizontal asymptote at y equals 1, and 2 magical vertical asymptotes at -2 and -1. Okay, the only other detail that we could possibly mention there is we could look at what happens to the graph as we approach those 2 vertical asymptotes, but we'll save those details for another time. Jumping on to our next example, provide a complete analysis of this function, x minus 2 over x squared minus 3x plus 2. Let's get factoring. So our numerator is going to be x minus 2, and our denominator will be x minus 2 times x minus 1. Okay, that stuff goes away doing the cancel dance, and so all we have is 1 over x minus 1. Alrighty, we have 2 non-permissible values here, at x equals 1 and at x equals -2. The one that cancels, remember, is going to create for us a removable or a point discontinuity. So our point discontinuity here is going to be at x equals 2. So we've got one of those. We should probably find the y-coordinate that's also not going to be allowed at that point. So we'd fill that into here. And if x equals 2, we get 1 over 2 minus 1, which is just 1. So our point discontinuity is going to be at 2 for x, 1 for y. Okay, let's check for asymptotes. We will have a vertical asymptote for this graph, and our vertical asymptote will occur at the root of the denominator that didn't cancel. So when x equals +1, we've got a vertical line that we'll get close to and never touch. Then we'll look for horizontal and oblique asymptotes. In terms of that, we look at the degrees, and since the numerator is of smaller degree, then the limit as x approaches infinity of our function f of x here is going to be equal to 0, which means we do have a horizontal but not an oblique asymptote. So our horizontal asymptote is at y equals 0. So there we go. Lots of neat stuff happening. The last thing we need to figure out for a complete analysis are our intercepts. So our x-intercepts are at roots of the numerator. So let's get those. Roots of the numerator here. 0 equals x minus 2. Uh-oh, no sir, because we saw over here that x minus 2 canceled out. It can't be an x-intercept if it's a non-point. So because of this, there are no roots of 1, so we have no x-intercepts again. Okay, so no x-intercepts for this function. Y-intercept, we'll get that one by finding f of 0. So we get f of 0, and that's going to be 0 minus 2 over 0 minus 0 plus 2, which is at -1. So our x-intercepts, there are none, and our y-intercept is at 0 and -1. So lots of stuff going on. Point of discontinuity at 2, 1, that's removable. We've got a vertical asymptote at x equals 1, horizontal asymptote at y equals 0, and a y-intercept at 0, -1. Lots of cool things on that function. Okay, one more. Provide a complete analysis of this function. Okay, let's get factoring. It's going to be x minus 2 times x plus 2 when we factor the difference of 2 squares that we have in the numerator. And our denominator is 2 minus x. Does anything cancel? Well, not on first glance, but let's take a careful look at this. Let's remember that if I have something like 2 minus x, and if I factor out a -1, that's the same as -2 plus x. So that's actually just the negative of, if I switch the order of these two, x minus 2. So 2 minus x and x minus 2 are almost the same thing. They're just negatives of each other. So over here, I can actually cancel out these two terms, and instead of getting 1 over 1, I'm going to get -1 over 1. Alrighty, so this function that we have here, f of x, hang on, this is just equal to a negative of x minus 2, sorry, x plus 2, which is minus x minus 2. And that's just a straight line. But we have a non-permissible value at x equals 2, so we're not allowed to actually be equal to 2. So basically what we have here is the graph of a straight line, and that straight line has a hole in it. So there's no asymptotes. We do have one point discontinuity. We can still find our intercepts, however. So let's get our x and y intercepts for this guy. X intercepts are going to be at roots of x plus 2 equals 0. So that means that x equals -2. We're going to have our x-intercept, and our y-intercept will occur at f of 0, and f of 0 in this case is going to be 0 plus 2. Okay, so it's -2. So our y-intercept is at 0 and -2. So we've got a straight line with a slope of 1, hitting -2 for x, -2 for y. Got a little hole in it at x equals +2. No asymptotes because it's just nice and linear. Okie dokie. Let's take a look at one exam type multiple choice question. It says, which graph matches the equation that's given? Well, the first thing I would look for in this is I would try to factor the equation I have as always. Then I'd check for vertical asymptotes and points of discontinuity or removable discontinuities, whatever we're calling them today. So we've got 2x divided by x outside of x plus 2. So these x's cancel. Alrighty. So that means we actually have a point discontinuity at x equals 0. So that's a good thing to note. And it looks like we're going to have a vertical asymptote when x equals -2. That might be enough information to find us a graph. It might not. We might have to go searching for more, but let's check. Okay. Point discontinuity at 0. Which one of these has that? Well, it's not this guy. This one's out. It doesn't have any holes in it. This one has a point discontinuity, but it's way over at -2. Wow, that's enough to get it already. Right here at x equals 0, we're in business. And the vertical asymptote at x equals -2, that looks like it's in the right place as well. So B is definitely our answer for this multiple choice question. Alrighty, here's the your turn question. Just like we did on several examples, provide a complete analysis for that particular function. I'm going to skip to the solution. You can pause if you want to work through it. So here is the solution in all of its gory detail. You can pause again and check your answers, read through it, and let's summarize everything that we've looked at in this particular topic. So things we've seen. For any rational function, we provide a complete analysis by using all the tools that we developed in the last unit about limits, continuity, asymptotes, all that good business. And we use the factored form, and we use the original form. So we use two different forms of our rational equation to give us all the information. So when we use the factored form, it tells us removable discontinuities, also called point discontinuities, vertical asymptotes, and our x-intercepts. And the original form can also help us determine horizontal and oblique asymptotes if we have to divide those out or check out the degrees. And by filling in x equals 0, we get our y-intercept. And that's everything you've ever wanted to know about rational functions, but we're afraid to ask. Hope you're having a good time studying. All the best on your exams. Keep watching if you think this is helpful.